Now we're going to look at the roots of complex numbers. This fact says that the complex number has n different nth roots, and we have a formula here for how to calculate those nth roots. So the nth root of z is obtained by taking the nth root of the lengths of z and then adjusting the angle that appears in the polar form of the complex number. Now we can see there's an alpha that comes up in the formula for the nth root. That alpha value is going to range between 0 and n minus 1 by letting alpha vary. That's how we're capturing the n different nth roots. So for example, if we were calculating the square roots of a complex number, there would be 2 different square roots, there would be 3 different cube roots, 4 different fourth roots, etc. So by letting the alpha values vary appropriately, we're able to calculate all those different nth roots. Suppose we wanted to find all the cube roots of -1. How we could start here is just by letting z equal -1, and we're just going to try to graph that complex number to see if we can figure out the polar form quickly. So if we were to graph z, z has a real part of -1, so that would just be going 1 unit to the left along the real axis, which is the x-axis. And that would allow us to quickly get our polar form because we can see that the length of z is 1, and we can figure out that the angle at which z is sitting is pi. So that allows us to write down our polar form. So length of z, 1, angle is pi, so we would write 1 times cos of pi plus I sine pi to get the polar form. Now that we've got that, we can apply the formula in the fact above to figure out what those cube roots are going to look like. So z to the 1/3, or in other words, the cube root of z, would be cube root of 1 times, and then we're going to modify the angle appearing in the polar form. So instead of having the angle pi, we're going to take our original angle pi, we're going to write plus 2 pi alpha, and divide by n. Well, in this case, n is 3 because we're calculating the cube roots. If we were doing square roots, n would be 2. If we were doing the fourth roots, n would be 4, etc. So in this case, cube roots means n equals 3. So cos of pi plus 2 pi alpha over 3 plus I sine of that same angle, pi plus 2 pi alpha over 3. The alpha values here are going to vary between 0 and 2. In general, you're going 0, 1, all the way up to n minus 1. So in this case, 0, 1, and 2. Now the hardest part of this calculation is just getting that angle simplified. So what we can do here is make a little table based on our 3 alpha values and just work out what pi plus 2 pi alpha over 3 actually simplifies to. So if alpha equals 0, then our angle would be pi over 3. If alpha equals 1, then we would have in the numerator pi plus 2 pi. So let's call that 3 pi over 3, which would simplify to pi. And if alpha equals 2, then we would have pi plus 4 pi over 3, or in other words, 5 pi over 3. You can write down the 3 different answers for the cube roots of z. In terms of notation, let's write z to the 1/3 with subscript 1 for our first answer, and then our other 2 answers similarly, we could use subscript 2 and subscript 3. So we're going to plug into the formula that we've got at the top of the screen there, just using the appropriate simplified angle as we go. So for our first cube root, well, cube root of 1 would be 1, and our angle simplifies to pi over 3. So 1 times cos pi over 3 plus I sine pi over 3, and let's simplify that. Cos of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2, so we'd have 1/2 plus root 3 over 2 times I for our first cube root. So again, for the second one, the cube root of 1 is 1. Our angle simplifies to pi. So we got cos pi plus I sine of pi. If we simplify this, cos of pi is -1. and sine of pi is 0. So that cube root just simplifies to -1. And for our last cube root, well, cube root of 1 is 1. Our angle simplifies to 5 pi over 3. So we have cos 5 pi over 3 plus I sine 5 pi over 3. And then let's evaluate. Cos of 5 pi over 3 is 1/2, and sine of 5 pi over 3 minus root 3 over 2. So 1/2 minus root 3 over 2i would be our third answer. So there we have our 3 cube roots of -1. So let's look at a different variation of this kind of problem. Say we wanted to solve x squared minus 2i equals 0. We could say x squared equals 2i, or x equals 2i to the 1/2, bearing in mind that there are going to be 2 solutions here. So when we calculate the square roots of a complex number, there are going to be 2 solutions. If we were calculating cube roots of a complex number, there would be 3 solutions, etc. So the trick here is to give a name to the complex number that we're trying to find the square roots of. So we should let z equal 2i. And that way we can say we're trying to find the square roots of z using that fact that we talked about previously. Let's graph z because we can probably figure out the polar form fairly easily from the graph. So remember that our imaginary axis is the vertical axis. So if z equals 2i, then we've just got a vector that's going 2 units vertically like that. We can look at that picture and say the length of z will be 2 units, and the angle at which z is sitting is pi over 2. So from there we can get our polar form. So in polar form, z equals the length of z, which is 2, times cos of the angle. So we're saying cos of pi over 2 plus I sine pi over 2 to get the polar form. From there, we can use our fact to write down what the 2 square roots would look like. So we'll say z to the 1/2 equals 2 to the 1/2 times, now we're going to have to modify the angle. So the angle inside the cosine becomes our original angle, which is pi over 2, plus 2 pi alpha, and that's all divided by n, where n describes the type of root that we're calculating. So if it's a square root, that would be n equal 2. Then we're saying plus I sine of that same angle. So pi over 2 plus 2 pi alpha all over 2. And the idea here is that the alpha value is going to vary, in general varying from 0 to n minus 1. So in this case, the alpha values would be 0 and 1, and those are going to generate our 2 square roots. So just like we did in the previous problem, let's make a little table of the alpha values and simplify the angle. So we want to simplify pi over 2 plus 2 pi alpha over 2. Well, if alpha is 0, then this looks like pi over 2 further divided by 2. So let's call that pi over 4. If alpha is 1, then we have pi over 2 plus 2 pi all over 2. And probably the easiest way to simplify that is to multiply top and bottom by 2. So if we multiply every single term top and bottom by 2, we'd have pi plus 4 pi over 4, or in other words, 5 pi over 4. So now we're ready to write down our 2 different square roots. So let's call these z to the 1/2, one with subscript 1, one with subscript 2, and let's figure them out. So we're just plugging into the formula that we've got at the top of the screen there. 2 to the 1/2 we could write as root 2, and then let's plug in the simplified angle. So we would have cos of pi over 4 plus I sine pi over 4, and we could simplify that and put that into rectangular form. So that's root 2 times 1 over root 2 plus I times 1 over root 2. So maybe best way to say that would be 1 plus I. For our second square root, it's exactly the same thing, but now we're using the angle 5 pi over 4 instead of the pi over 4. So if we simplify this, we've got root 2 times cos of 5 pi over 4 is going to give us the negative 1 over root 2. And sine of 5 pi over 4, same thing. So we end up with minus 1 over root 2 times I. And by the time we've multiplied through by the root 2, we end up with negative 1 minus I. So that gives us our second square root. So we could leave our answer like this, or we could recognize that we were solving the original equation for x. So if we wanted, we could say x is equal to plus or minus, and then in brackets, 1 plus I.